The chemical turning point nobody was prepared for. It happened quietly. No countdown, no public warning. Just a shift in chemistry that permanently altered how the world would function. Most turning points are only obvious in hindsight. At the time, this one looked like progress as usual. A new method, a better reaction, a solution to an existing limitation. But beneath the surface, chemistry had crossed a threshold humanity did not yet recognize. To understand why this moment matters today, we need to look at how change truly occurs in science. Breakthroughs rarely announce consequences. They solve immediate problems first. The long-term effects emerge later, often after systems have already adapted around them. At first, the new chemistry seemed manageable. It behaved predictably under controlled conditions. It integrated smoothly with existing processes. Nothing appeared unstable. In fact, it improved reliability and efficiency. But what made this turning point different was scale. The reaction did not remain specialized. It spread rapidly, embedding itself into multiple industries at once. What had once been optional became foundational. This is where the story begins, with a chemical shift so seamless that no one paused to ask what would happen when the entire world started relying on it at the same time. As adoption accelerated, the chemistry moved from innovation to infrastructure. Systems were redesigned around it. Training adapted. Supply chains aligned. The reaction stopped being a choice and became an assumption. What made this shift dangerous was familiarity. Once a reaction becomes standard, it fades into the background. No one questions its limits. No one plans for its failure. Chemistry becomes invisible again, even as dependence deepens. Early signals appeared, but they were easy to dismiss. Minor inefficiencies, unexpected interactions, small adjustments required to keep things running smoothly. Nothing dramatic enough to slow momentum. Behind the scenes, however, chemistry was behaving differently at scale. Reactions overlapped. Byproducts accumulated. Feedback loops formed where isolation once existed. The system still worked, but it was no longer stable in the same way. Scientists studying these patterns noticed a troubling trend. The chemistry was no longer self-contained. Changes in one area propagated elsewhere. Local optimizations produced global side effects. This is where tension takes shape. The turning point had already passed, but recognition lagged behind. The world was now committed to a chemical pathway it barely understood at full scale. The reaction continued to deliver benefits. That was the problem. Success delayed scrutiny. And chemistry, patient and exact, continued responding to conditions exactly as designed. The conflict emerged when stability began to erode in subtle ways. Systems still functioned, but margins grew thinner. Tolerances tightened. What once absorbed variation now reacted sharply to small disruptions. Chemistry revealed a critical weakness. The turning point reaction worked best under ideal conditions, yet the real world rarely offers ideal conditions for long. Temperature fluctuations, material inconsistencies, and human behavior introduced noise the chemistry was never meant to handle continuously. As dependence deepened, flexibility disappeared. Backup methods faded. Alternative reactions were abandoned. The system optimized itself into fragility, efficient but brittle. This buildup carried emotional weight because the warning signs were clear to those looking closely. Scientists saw correlations forming. Small failures shared common chemical roots. Local problems echoed each other across distant systems. Attempts to intervene faced resistance. Changing course meant redesigning infrastructure. Admitting risk meant admitting oversight. The reaction had become too embedded to question easily. This was the moment before realization, when chemistry had already locked in outcomes, but society had not yet acknowledged the cost. The turning point was no longer theoretical. It was unfolding in real time. What once felt like progress now felt like pressure, and chemistry, indifferent to expectation, continued enforcing the consequences of earlier choices. The climax arrived not with collapse, but with recognition. The understanding that the chemical turning point had already reshaped the rules, and there was no simple return to before. This realization changed the conversation. The problem was no longer about fixing a single reaction. It was about redesigning systems that had grown around it. Chemistry had not failed. It had succeeded too completely. The resolution lies in resilience, reintroducing flexibility, diversifying reactions, designing pathways that tolerate uncertainty instead of denying it. Chemistry guided not by maximum efficiency, but by long-term stability. This moment became a lesson written into modern science. Every breakthrough carries a shadow. Every improvement shifts balance somewhere else. The question is not whether chemistry will change the world, but whether we are prepared for how it changes us. Understanding this turning point gives us a rare advantage: foresight, the ability to pause before scale locks in again, to ask harder questions earlier, to treat chemistry as a partner, not just a tool. What happened here was not an accident. It was a pattern, and patterns can be recognized, learned from, and reshaped. Sometimes the smallest shift in perspective becomes the beginning of a new future.